Good morning, students. In this session, we will try to explore more the fundamentals about the stagnation states, which are very quite common in gas dynamics course. So, for this, the basic fundamentals starts from thermodynamics, where we are dealing with steady flow energy equation. So, we already know the basics of steady flow energy equation, and I am going to write the same in the screen. H1 plus half C1 squared plus GZ1 plus Q12 is given H2 plus half C2 squared plus GZ2 plus W12. It is better even to put equal to, this particular equation is known as the steady flow energy equation, which have been arrived from the first law of thermodynamics applicable for an open system, which says that Q equal to W plus delta E. To get more information about this particular steady flow equation, you can go through the previous video which we have already provided. For this particular section, for the stagnation states and stagnation enthalpy, we will proceed further. So, stagnation states and stagnation enthalpy. So, in the above equation, we can see here H1 stands for the static enthalpy, half C1 squared is for the velocity component or the kinetic energy, GZ1 is for the potential energy, and the Q12 is the amount of or the rate of heat transfer, and W12 on the right hand side is the amount of work transfer. Similarly, the H2, C2 on the GZ2 are the corresponding enthalpy, kinetic energy and potential energy terms. From this, now we are going to arrive what is meant by stagnation enthalpy. Okay, so in the above equation, in most of the gas dynamic application, especially in the aerospace industry, there is no work done. For example, we can consider a nozzle. So, if I consider a nozzle, a convergent divergent nozzle like this, I can see there is the flow will be entering through the inlet and it will be leaving at the exit. So, let us call this as 1, this as 2. Here the 1 indicates the inlet and 2 indicates the outlet. Here the gas, the combusted gases with a lot of energy is coming through this convergent divergent nozzle and leaving at section 2, and leaving at section 2. Here there is no rotating components and hence the work done is 0, which means W12 can be made 0. And we assume there is no heat loss from this gas from the system to the surrounding or from the surrounding entering into the system, which means Q12 can also be made 0. And here the datum or the height, the potential energy can also be neglected because Z1 is equal to what? Z2. Z1 equal to Z2, and hence I can cancel off, Z1 and Z2, this half C2 squared will be there. Now the above steady flow energy equation get reduced to H1 plus half C1 squared is equal to H2 plus half C2 squared. This corresponding equation is called as adiabatic energy transformation. So, I can write this equation as what? Adiabatic energy transformation. So, this equation is very simple. Now, you see the fluid is coming or the combustion gases is coming with an energy of enthalpy H1 with a velocity say C1 and is going to leave at an enthalpy say H2 and velocity C2. The main objective of a nozzle is to increase the kinetic energy, which means C2 should be greater than what? C1. When C2 is greater than C1, when C2 is going to be greater than C1, automatically what will happen? H2 will get reduced compared to H1. Compared to H1 will be more and H2 will be reduced because the total energy is conserved. If one form of energy is going to convert to another form, show C2 is more than C1, which means H2 should be less than what? H1. So we also know that the static enthalpy or H is given by U plus PV, which means here the P indicates the pressure. Here the pressure energy is converted into what? Kinetic energy. So we can conclude that in a convergent divergent nozzle or a convergent nozzle, the pressure energy is converted into kinetic energy. So this is a very fundamental equation, and this is called as adiabatic energy transformation. And why we are calling it as adiabatic means because there is no heat loss from the system. See here the system is nozzle, from the nozzle to the surrounding, or there is no heat is getting from the surrounding into the system. As we are discussing about the adiabatic energy equation, we can recall H1 plus half C1 squared is equal to H2 plus half C2 squared. Now coming to the stagnation conditions or stagnation states, we will define what is stagnation states or stagnation enthalpy. Now in the previous example we have seen in a nozzle the flow is entering at 1 with an enthalpy of H1 with a velocity of C1, and it is existing or going out with a enthalpy of H2 and a velocity of C2. What is meant by stagnation? I am going to make the flow to stagnate. Now the flow is coming from the left hand side to the right hand side, and at a particular location I am going to make this flow to stagnate, which means I am going to make this flow to come to rest, which means my C2 is brought to 0. My C2 is brought to 0. So you can see the flow is entering at H1 and is trying to come at exit at velocity C2. But I am going to make this C2 equal to what? 0. It can be a nozzle, it can be a diffuser, it can be heat exchanger, it can be a chimney. So it can be any open device. But finally, if I am going to make the flow to stagnate after a particular condition, is called as what? Stagnation state. This stagnation state is possible when you are going to adiabatically decelerated. Now the condition is imposed. What is the condition? That we are not simply going to make the flow to become 0 velocity, but we are going to decelerate adiabatically. What is meant by adiabatically? There is no heat transfer from the system to the surrounding or from the surrounding to the system. So we have to include that word. That word is very, very important. Adiabatically decelerated. To what? To 0 velocity. Then only it become what? Stagnation. Okay. To 0 velocity at 0 elevation. At 0 elevation. Which means my C2 equal to 0. And here we can call this H2 as H0. What here the naught indicates? Stagnation. Here the naught indicates you the stagnation. So we can see that when C2 is brought to 0, H2 takes the form of H0, where H0 is called the stagnation enthalpy. Now we can see H1 plus half C1 squared equal to what? H0. Since there is only one variable involved now, what are these? At state 1 only, either H1 and C1. There are two variables, H1 and C1, but at a one condition only, at one state only. So it's enough to simply say H plus half C squared equal to what? H0. So you may be asking a question, sir, why you have not put 1? I am from 1, I am going to make the flow to be what? C2 equal to 0. This, let us say this is at state 1. From 1, I am going to make the flow to get stagnate at point 2, where the velocity is brought to what? 0. It need not to be. What is need not to be? There is no need for me to start from 1. I can start even from this location. Let us say this location is 3. Now also, I can make the flow to brought to rest at what? The condition say 2. So the inlet location is not mandatory. It can be either at 1, it can be at location 3, it can be at location 5, anywhere. So now it is not with respect to the state points, it can be from any location. So you can take the variable. So that only I replace H1 plus half C1 squared equal to H0 as H plus half C squared equal to what? H naught. Now my dear students, can you comment on this statement? What is called as H? What is called as H naught? Here H is called as the static enthalpy. H naught is called as stagnation enthalpy. H is called as static enthalpy and H naught is called as what? Stagnation enthalpy. One more beauty in this equation is, can any one of you can tell me how many variables are there, how many constants are there? I will repeat the question. In this equation H plus half C squared equal to H naught, how many variables are there, how many constants are there? So we can see there are two variables. What are they? H and C. If I am going to locate at 1, it will have H1, it will have C1 squared. If I am going to locate at 3, it can take H3, it can be different, C3 squared. But always the H naught remains constant. The final stagnant state remains constant. So the right hand side H naught is constant, whereas H and C, which are on the left hand sides, are variable. So H plus half C squared equal to what? H naught. This is the equation called as stagnation enthalpy. Here H naught is called as the equation for stagnation enthalpy. Let us move on to the next page. So we got now H naught equal to what? H plus half C squared. We also know that H is given as what? CPT. H is given by what? The formula CPT. Then many students have a doubt. What is capital H? Capital H equal to MCPT. What is the difference between small h and capital H? Small h is called as specific enthalpy. Its unit is kilojoule per kilogram or joule per kilogram. Whereas the unit of H is only kilojoules or joules. So the unit of capital H is what? Kilojoules. Similarly, some students will ask me a doubt. So what is delta H? Then what is the formula? Yeah, MCP delta T. If there is a delta H, there is a delta T. What is delta T? T2 minus T1. Final minus initial. So you should know, all the students should know what is the meaning of these three terms individually. As well as what is then H naught? Can you tell me what is H naught now? The formula for H naught? Yes, you are right. It is Cp and T naught. Yeah. It is not T. Since the suffix is H naught, the T should also be what? T naught. So H naught equal to Cp into T naught, where T naught is called as, what is T naught? Yeah, you are right. T naught is called as stagnation temperature. Now we are trying to evolve what is the meaning of stagnation temperature. What is T then? T is called as static temperature. T is called as what? Static temperature. So now we can substitute for the values of H and H naught. Let us we'll substitute 2 and 3 in 1. So we'll end up with Cp into T naught is equal to Cp into T plus half C squared. And some of my students will ask a doubt. Sir, you told this is stagnation enthalpy, this is static enthalpy. Then how we can call this term? We can call this term as dynamic enthalpy also. Because the stagnation enthalpy is also known as what? Total enthalpy. So the total enthalpy will be equal to what? Static enthalpy plus dynamic enthalpy. So we can call this term also as what? Dynamic enthalpy, or the term which will correspond to the dynamic portion of the enthalpy. Very good. Now we got the equation as what? Cpt naught equal to Cpt plus half C squared. Now divide this entire equation by Cp. What is Cp? Specific capacity at constant pressure. Specific heat capacity at a constant pressure. So T naught equal to what? T plus half C squared by Cp. I have divided the entire equation by Cp. Now let us move on to the next slide. So we have T naught equal to T plus 1 by 2 into C squared by Cp. What is Cp, or what is the relationship between Cp and Cv? We already know in our school standards Cp minus Cv equal to what? R, where R is called as the characteristic gas constant. And also we know that Cp by Cv equal to what? Gamma. The ratio of specific capacity equal to gamma. So from these two expressions, from let us say this is equation number 4, this is equation number 5. So from 4, I will take Cp as common. So 1 minus Cv by Cp equal to R, or Cp into 1 minus Cp by Cv equal to gamma. So what is Cp by Cp? 1 by gamma is the reciprocal of gamma. So 1 by gamma equal to R. So it is Cp into gamma minus 1 by gamma equal to R, or Cp is equal to gamma into R by gamma minus 1. So we got the value of Cp, R gamma by gamma minus 1. Okay. Now we will continue further. I will make a small partition here. I will divide even this equation by T. So T naught by T is equal to 1. I am dividing the entire term by what? Entire equation by T. So T naught by T equal to 1 plus 1 by 2 into C squared divided by Cp into T. I am dividing this also by T. Now try to substitute for Cp. What is Cp? Gamma R by gamma minus 1 into T. I can take this gamma minus 1 now to the numerator. So T naught by T will be equal to 1 plus gamma minus 1 by 2 into C squared by gamma RT. And here, students, you should know that A squared equal to gamma RT, or A equal to square root of what? Gamma RT. So you may wonder what is A. A is nothing but the velocity of sound. A is nothing but the velocity of sound. And C is the velocity of the fluid. Fluid means the velocity of your aircraft, velocity of the object, because the relative velocity. So C is nothing but the velocity of the flight, and A is the velocity of the sound. Both are the velocities. So this term will derive in future how we got A square as gamma RT and not now. So we will take this gamma RT as what? Now A squared. So T naught by T will be equal to 1 plus gamma minus 1 by 2 into C squared by A squared. Also we know that, what we know that the Mach number or the Mach number is given by C by A. It's a ratio of the velocity of the fluid to the velocity of the sound in air, generally, because the flight is going to travel in air. So we will call it is M equal to C by A. If it is going to travel in other medium, according to the A will also vary, but generally the Mach number is different for the flights, and hence it will travel in the air. So M equal to what? C by A. So we can see here the C squared by A squared will become M squared. So finally we end up T naught by T equal to what? 1 plus gamma minus 1 by 2 into M squared. So this is the final expression for the stagnation temperature. Here T naught indicates the stagnation temperature, T indicates the static temperature, gamma indicates the ratio of the specific capacity, and it mostly be considered as a constant. And here the M is nothing but the Mach number. M is nothing but the Mach number. To have one more better understanding, we'll go to the next slide. So we can see here T naught by T equal to what? 1 plus gamma minus 1 by 2 into M squared. So here the variables are T and M only. T naught is a constant. As H naught is constant, T naught is also constant. Stagnation enthalpy and stagnant temperature is a constant, whereas T and M are variables, which means I can write like this. When T becomes T1, my M becomes what? M1, which is nothing but T naught by T1 will be called as what? 1 plus gamma minus 1 by 2 into M1 squared. Got it? What is M1? The Mach number at the inlet. What is M2? The Mach number may be at the exit. Okay. So we can see with respect to temperature, the Mach number, there is a relation between T1 and M1 with respect to T naught and gamma. That is what we derived. Similarly, if I am going to put T equal to T2, my M will become what? M2. So T naught by T2 will be equal to 1 plus gamma minus 1 by 2 into M2 squared. It can be M3, M4, M5, whatever you want. So it's a variable. It's a variable. So generally, to conclude, from the next class onwards, we will proceed with this equation. T naught by T equal to what? 1 plus gamma minus 1 by 2 into n squared. So please make a box and memorize also. These equations also available in the standard gas tables also. So there's no need to by heart, but you should know the physical meaning of this equation. Here T naught is the stagnation enthalpy, stagnation temperature, T is the static temperature, and M is the Mach number. I hope you enjoyed what is known by stagnation states. The flow is adiabatically brought to rest or decelerated to rest at zero velocity at zero elevation, and the corresponding enthalpy is called stagnation enthalpy. From this stagnation enthalpy, we are able to derive the stagnation temperature as well as its ratio with respect to the static temperature. I hope you enjoy the lecture. Thank you.